Our next speaker is Elke Neu-Ruffing, and please take it away.
Yeah, thanks a lot for the introduction. So our this talk is going to be about diamond nano-quantum sensors. I'd like to summarize our research on this topic, and the outline of the talk is, as you can see here. I'd like to give you a very brief introduction why we use color sensors and diamond as sensors. I want to talk a little bit about the nanotechnology that you need to fabricate such a sensor, and what you can do about optimizing and scaling such sensors. And in the last few slides, I'd like to show you a very novel field of application of those sensors, which is sensing using optical near fields. Okay, so let's start right away with why do we use those color sensors in diamond as sensors. The color sensors are defects in the diamond where you have just changed the lattice in one or a few neighboring lattice sites. The most prominent color center is the so-called NV center. So you have a nitrogen replacing a carbon and a vacancy. This forms the defect. And for us, this defect is an artificial atom. So it more or less acts like an atom. You have electrons bound there. It is very stable, which is good for a sensor. And the point that we like to use is that it has very long-lived and highly controllable spin states, which makes it an interesting system for a magnetic sensor. Apart from this, I should also say that the host material, the diamond itself, is interesting for us here because it's very transparent. So you can easily extract light from it. It's biocompatible. It has a high mechanical hardness. And if you go into detail, well, diamond is carbon. Carbon is mostly C12, and the C12 is a spin-free isotope, so you have not a lot of spins, and this makes it good as a host for a magnetic sensor. In our case, this is a quite special way of using such color sensors as sensors, and this is so-called scanning probe imaging. So we do incorporate the color sensor into a device that looks like an AFM tip, and we scan the sample with this. It is a highly non-invasive sensor. You have only this single color sensor as a magnetic sensor. You get a very high sensitivity because you can get as close as tens of nanometers here to the sample. And because you have this very tiny, this atomically small sensor, you can get a very high resolution, which is only governed by the distance here of the color sensor to the sample that you are imaging. How does the color sensor work? So on the one hand, in the ground state of this NV center, you have three different spin states, the 0, the plus, and the -1. And due to internal dynamics, if the system is in the 0 state, it will emit a brighter fluorescence than in the two other states. You can drive the transitions between those states with a microwave and read out the spin state then optically because of this difference in fluorescence here. It is what we call optically detected magnetic resonance, and these, especially these plus and -1 states, undergo a Zeeman shift. So the difference between the transition from 0 to +1 and 0 to -1 tells you which magnetic field has been applied to the NV center. Like this, you can use a single NV center as a sensor. The sensitivity scales with the photon rate, so you always need to get a good optical readout. On the other hand, your color sensor is also an electrical dipole. As an emitter of light, it has to be an electrical dipole. And as this, it can exchange energy with other dipoles that are close by. This is a process called Förster resonance energy transfer, or short FRET. You have one dipole, this is a donor, that will be excited, but instead of directly radiating, it transfers its energy to an acceptor. And this process is highly distance dependent. It scales with 1 to the 6th power of the distance. So you can use this also as a tool for nanoscale imaging of the presence of other dipoles. Let me give you two illustrative examples of those two imaging modes or sensing modes. So one is given here. You can see here the magnetic field of a nickel nanorod, which we have imaged with such a scanning NV tip. You can see we get a quantitative imaging, and we see here a quite high resolution. You can see changes of the magnetic field within approximately 10 nanometer. On the right part of the slide, you see a very simple example of such a thread transfer. We put some graphene onto a diamond with a layer of NV centers, and you can see the excited state lifetime of the NV centers is reduced in areas with the graphene, and this is to the fact that the energy flows from the NV center to the graphene, and this is an example of such a near-field transfer. The question is, does this both work in parallel? I will show you in the end. Yes, indeed, you can make truly multifunctional sensing here. Okay, now let me quickly say something about how you can do such a diamond AFM tip and what you have to keep in mind here. First, you have to keep in mind diamond has a very high refractive index, 2.4. So most of the light of the color sensor just stays in the diamond because of total internal reflection. And the nitrogen vacancy center has a quite broad emission band, roughly 100 nanometer of emission width. So you want your AFM tip to be a photonic structure that efficiently extracts the lights and also works with this broad emission. This is important. And the two types of structures we are typically working with is pyramids. So this is really what you think of when you think of a tip, and cylindrical nanostructures that we call pillars. These pyramids, they are typically formed by growing. So you put it in you use a chemical vapor deposition, grows of diamond, and this forms a pyramid that you can see here. So you take a pillar, you overgrow it to form a pyramid. If you do calculations, you see that for NV centers placed close to the apex of the tip, you get the best collection efficiency, so the most efficient sensor readout. This is very good. However, it's very hard to place the color centers here. So we are typically still working with the other approach, that you do not grow the structures but directly produce them during nanofabrication, where you start with an ultra pure diamond and you form a device that looks like this. You have a mounting structure here and a cylindrical nanopillar here and the NV center here in the, well, in this case, flat tip then. This needs a lot of nanofabrication. You start with a polished membrane, you thin it down via etching, you create NV centers by ion implantation, and then you do two structuring steps with electron beam lithography and plasma etching to form this device here. And in the end, you mount it to, in principle, an AFM to enable the scanning of the sample. I don't want to go into details of the nanofabrication process, just to let you know that it is not so straightforward, because diamond is a not straightforward material. So you need very sophisticated etching plasmas. You need to make sure that everything you put on here adheres to the diamond. And this has cost us some time, but we have now a working process, and we can produce larger arrays of these devices, several hundreds of those devices. You see here the pillar, you see the mounting structure, and maybe it's best to see here. This is just connected with a weak link to the rest of the sample, because we now want to pick one of these tips and bring it into our AFM to do the measurements. This you can see here. Here it was connected to the rest of the sample, and this connection has been broken. It has been broken by gluing the device to a quartz capillary and then just pushing, and you break it off of the rest of the devices. And here's the pillar facing down towards the sample. This really works with micro manipulation, bringing the capillary in contact, gluing it, and then you have one device here that you can mount to a tuning fork based AFM, and you can do the scanning NV measurements with it. So this is the principle of all these experiments. And I want to say some words about what we can do about optimization and scaling. First, you might have realized the pillars are not perfectly cylindrical. If you simulate it, also this little bit of a truncated cone that we have works very nicely, considering the photonics. And the second remark I want to make on this is that we are now trying to scale this process up. So far we are processing very small diamonds of just some millimeters, but in 2018 the group of Matthias Schreck in Augsburg has presented the first diamond wafer here, single crystal diamond wafer. This is done by a so-called heteroepitaxial diamond, and we have also used this to make such pillars. It works very nicely, and this material is now getting pure enough so that we see single nitrogen vacancy centers here, these dots, in the material. So we are really hoping that in next years you can also scale this up, make more diamond tips, larger structures, and so on, using the so-called heteroepitaxial wafer diamond material. Okay, so far for the introduction and the device itself. Now let me show you this novel idea on using the near fields for sensing. And we have choose here a model system for this thread transfer. The NV center is the donor and the acceptor is tungsten diselenide. This is a two-dimensional graphene-like material, but it's a luminescent material. And we choose it because we here get the required overlap of the absorption and emission bands that you need for the thread process. And in collaboration with Igor Aronovich in Sydney, his group transferred some of these tungsten diselenide flakes onto a diamond, which has a layer of NV centers. And now we want to observe this thread transfer between the NV centers and this luminescent material. So if you look first at the sample, you see areas with very bright luminescence, the green yellowish ones here. You can see already here the triangular shape, for example. So these very bright areas are the tungsten diselenide flakes. The weaker fluorescence in between is the fluorescence of this layer of the NV centers. And now you switch to the lifetime imaging. So here you image the excited state lifetime of the NV centers. And you can see here, well, you get almost the same picture. Where such a flake has been positioned, you see that the lifetime of the NV center is going down. So you see clearly this transfer of energy from the NV center to the tungsten diselenide flakes. And for the experts, we have calculated so-called Förster radius of 13 nanometers, where this is the point where the efficiency of the transfer is 50%. So it's a quite efficient transfer. And now is the question, the NV centers in these regions here, would they still work as a magnetic sensor? Would they still react to magnetic fields? And the answer is yes. We can still see this optically detected magnetic resonance if we drive the NV spin with the correct frequency. And we can also see that it still undergoes the Zeeman splitting and indeed reacts to magnetic fields. So you can combine these two processes. Even this thread is a very strong change in the dynamics. Still, you can use the NV as a magnetic sensor. And we are currently working on broadening this. We have now new samples with molybdenum diselenide flakes. They form these little stars here. Again, we see the reduction of the lifetime, as you can see here, now in the darker areas. And we have now better samples where we can also clearly distinguish between the NV and the molybdenum diselenide fluorescence. And we can make more sophisticated spin measurements, and we are currently working on seeing the effects of this two-dimensional material on the coherence time of the NV spin, not just on the optical lifetime. And this is very interesting also to see if you can really combine this with the thread, still see the coherence of the system. Okay, with this, I'd like to summarize my talk. So I've shown you a bit of the work on our diamond nano-quantum sensor, which mainly boils down to devices that look like this mounting structure with a pillar. There's still a lot to do in optimizing the nanofabrication and scaling it. The thread process, we are currently investigating this as a novel sensing resource so that we can use NV centers not just as spin-based sensors, but also as dipole-based sensors. And I hope that from those research, a variety of applications will arise in life sciences, in material sciences, and so on. And with this, I'd like to thank you for your attention.
Thank you very much, Elke. We have one question already from Peter Koch. He asks, how does the NV sensor compare to current AFM sensitivity?
You mean for the magnetic fields? So we don't have the highest sensitivity here in sensing, I should say. So typically, if we just look at this shift of the resonances, we get a microtesla per square root of hertz. So means within 1 second you can measure a change for static field of a microtesla. If we have oscillating fields and we can do this coherence-based sensing or AC sensing, we go down to nanotesla. So this is what we can do at the moment. We can get more sensitivity if we sacrifice resolution. So the closer the NV is to the surface, the worse the sensitivity, but the better the resolution. Yeah? So this is a bit of the compromise you have to do for those sensors, actually.
Okay, thank you very much. So the floor is open for questions. Please submit any that you have. In the meantime, I have a couple of colleagues who work in this kind of field. Is a lot of the work to make these devices a lot about trial and error and just trying to grit your teeth and go for it?
Yeah, it's indeed, you cannot use any standard recipe because diamond's not a standard material. Huh? So you have to design your own etching recipe, and it's often hard to get all these structuring layers you need. This resist stick to the diamond. So this was the problem that we have overcome in this process that we filed for patent. But yes, indeed, it is hard to do. But I should also say that there are now 2 companies in Switzerland that are also selling the first commercial tips on this. So it's not anymore absolutely necessary that you master the nanofabrication, I should say.
Brilliant. Yeah, so there's a route to market even already.
Yeah, exactly. So in last year, the first commercial devices and also commercial tips have been launched to the market. So I think this can expand a lot more in the next years.
Fantastic. Okay, so if anyone has any further questions for Elke, please use the chat, or I guess your email's available as well, Elke.
Yeah, exactly. It's on the slide there.
Perfect. So thank you very much.